Hello and welcome you to the lecture about instruction cycle. According to the definition, program has a set of instructions and each instruction follow a particular cycle which in turn gets subdivided into sub-cycles. The cycle is 1. Fetch. 2. Decode. 3. Execute. Fetch instruction cycle. Fetch cycle is the first step of the instruction cycle. The address of the first instruction of the program gets loaded into the program counter or PC. Then the value of the sequence counter or SC is made 0 and a decoding timing signal T0 is sent. SC will get incremented by 1 with each clock pulse, and thus there will be a sequence of timing signals T0, T1, T2, and so on. We can define fetch and decode phrases by writing the micro operations for them. T0 is to PC moves to AR. T1 is to M into brackets AR moves to IR, or PC plus 1 moves to PC. T2 is to decode IR into brackets 12 to 14 is to D0 to D7, or IR into brackets 0 to 11 is to AR, or IR15 is to I. The address from PC is transferred to AR during the clock transition associated with timing signal T0 because only AR is connected to the address inputs of memory. The instruction read from memory is then placed in the instruction register IR with the clock transition associated with timing signal T1. PC is then incremented by 1 to prepare it for the address of next instruction in the program. At time T2, decoding of the instruction code which is stored in IR takes place and the indirect bit is transferred to flip-flop I. Also, the address part of the instruction is transferred to AR. After each clock pulse, SC will be incremented so as to produce the sequence T0, T1, and T2. In first to register transfer statement in the bus system, to provide the data path for the transfer of PC to AR, we need to apply timing signal T0 to achieve the following connection. 1. Bus selection input S1, S2, S3 are made to 010 so that the contents of PC are placed onto the bus. 2. Load or LD input of AR is enabled to transfer the content of the bus to AR. On the next clock transition, T0 will become 1 and this will initiate the transfer from PC to AR. To implement the statements at T1, that is, placing the instruction into instruction register, which is read from memory, and to increment the PC by 1. Timing signal T1 is used to provide the connections in the bus. These are 1. Read input of memory is enabled. 2. Value of S1, S2, S3 will be 1, 1, 1 for placing the contents of memory onto bus. 3. Contents of bus will be transferred to IR by enabling the load or LD input of IR. 4. Increment PC by enabling the INR input of PC. At the next clock transition, T1 will be 1 and read and increment operations are initiated. In figure 1, multiple input OR gates are included as other control functions can initiate similar operations. Type of instruction determination. T3's timing signal will be active after decoding. Type of instruction that was just read from memory is determined during time T3. The flowchart for initial configuration for instruction cycle and determining the type of instruction is given in figure 2. There are three possible types of instructions present in the basic computer, and these are: 1. Memory reference instruction. A memory reference instruction uses 12 bits to specify an address and 1 bit to specify the address mode I. That is, mode I will be 0 for direct address and 1 for indirect address. 2. Register reference instruction. The register reference instruction is recognized by the operation code 111 with a 0 in the leftmost bit of the instruction. A register reference instruction specifies an operation on or a test of the AC register. 3. Input-output instruction. An input-output instruction is recognized by the operation code 111 with a 1 in the leftmost bit of the instruction and does not require a reference to memory. If operation code is equal to 111, then the decoder output D7 is equal to 1. It is shown in figure 2 that if D7 is equal to 1, then the instruction is either an input-output instruction or register reference instruction. If D7 is equal to 0, then the operation code is between 000 through 110 and it specifies a memory reference instruction. Flip-flop I then contains the first bit of the instruction and it is inspected by the control. If D7 is equal to 0 and I is equal to 1, then it is memory reference instruction with an indirect address. The register transfer statement M into brackets AR moves to AR is used as symbolization for the indirect address condition. AR stores the address part of the instruction which is used during the memory read operation. Then the word stored at this address is read from memory and placed on the common bus. The load input of AR is then enabled to receive the indirect address that resided in the 12 least significant bits of the memory. These 3 instruction types are then further divided into 4 separate paths. The operation which is selected is activated with the clock transition associated with T3 timing signal. We can symbolize them in the following manner. D7I, T3 is to nothing. D7I, T3 execute a register reference instruction. D7 IT3 is to execute an input-output instruction. When memory reference instruction with I is equal to 0 is encountered, it is not required to do anything since the effective address is already in AR. However, when D7T3 is equal to 1, SC is incremented by 1 to continue the execution of memory reference instruction with timing variable T4. A register reference or input-output instruction can be executed with the clock associated with the timing signal T3. When the instruction has been executed, SC is set to 0 and the control is returned to the fetch phase with T0 is equal to 1. Note: with every positive clock transition, sequence counter or SC is either incremented or cleared to 0. That brings us to the end of this section. Thank you.